So before we begin, if you have any question, you can ask now. Okay, so in the last class, what we were discussing is about the structure of the crystal, so where we have a regular arrangement of atoms, which we can represent using a unit cell, and by repeating that unit cell, we can create the crystal. However, the crystals are always not perfect. So there are defects, they have defects, and we looked at one kind of defect, which is known as a point defect or a vacancy. And we also saw that you can also have vacancies where there is no atom. You can also have, you can substitute some impurity atoms in place of those in place of those vacancies, and those impurities in semiconductors, one can do it in a controlled way, which we call as doping. And then we also saw how one can find a difference between no, I haven't shared the slides yet, so I will share now. And then also we discussed about like polycrystalline, what is a polycrystalline material and a single crystalline material. So single crystalline, or sometimes it is known also as monocrystalline material as well. So let me share. And today, so we briefly started with this to distinguish materials based on their electrical conduction. So we will continue with that. Okay, so when we want to talk about the electrical conduction, what we say is the flow of electrons. So you have flow of electrons in presence of electric field. So this electric field you represent, or you say it is like a voltage that you apply to the sample, and in response to that, so you have a flow of electrons or charges, which gives rise to a current I. And the relation between your voltage and current is given by Ohm's law, which is V is equal to I into R, and R is the resistance of the material, which depends on actually the dimensions of the material using this following relation. So where rho is your resistivity, so L is the length, and A is your cross-sectional area. And this resistivity is doesn't depend on the dimension of the material, so that means it doesn't depend on length and the cross sections, and therefore you can actually compare different materials based on their resistivity. And what we saw is, like, if you take a metals like copper or silver, sorry, uh, copper or silver or gold. Okay, so these are really a low resistivity, which is of the order of so 10 to the power minus 9, and normally you represent it in units of ohm meter. Uh, and then you have semiconductors, so like silicon, then germanium, gallium arsenide, so where the resistivity can vary actually between a wide range. It can vary something by 10 to the power 4 to 10 to the power uh, minus 4 ohm meter, and this large variation is due to the possibility that you can dope these semiconducting materials. And then you have insulators. For example, you have Teflon, or you have diamond. Okay, so where your typical resistivity will be more than 10 to the power 6 ohm per meter. So, so these are typical values based on which you can distinguish or say that whether the material will conduct electricity or not. However, uh, it is not only the absolute values that you look at, but what you look at is the temperature dependence of the resistivity as well. So if you look at the temperature dependence of rho, so that tells you a lot more about the material, what kind of conductivity is happening in the material, so that you can tell uh, or define in a better way. And therefore, uh, so if you plot the resistivity, so as a function of temperature, so for a metal, so the dependence looks like this. Okay. Now, if I take, so this is for a metal. Now, if I take a semiconductor, so resistivity will decrease as you increase the temperature. So this is a semiconductor. And an insulator will basically behave similar to a uh, so insulator will be similar to a semiconductor, but it will have a higher value of resistivity compared to your insulator. So this is a typical resistivity as a function of temperature. So we have plotted it from really high temperature to almost low temperature, like if you go really close to the absolute zero temperature. So this temperature dependence, so let's, yeah, there is one interesting material which you might have heard of, but we will not really discuss in this course, but I want that you know about it. So there is another kind of material known as superconductors. So you probably would have heard of it. So superconductor are nothing but they are the perfect conductors. Like they have the resistivity is zero. So we have superconductor. These materials have resistivity is zero below certain critical temperature. Tc. So Tc is a critical temperature. So below Tc, the resistivity of a superconducting material will vanish, and normally it is represented by, so we can plot it here as well. Okay. So if you plot a resistivity as a function of temperature of a superconductor, so it will be something like this, and this temperature value is Tc. So and this Tc, like a typical value of Tc for uh, let's say, yeah, lead, for example. So all materials do not become superconductors. So So some metals, they become superconductors. So for example, lead is one example where Tc is about 4.2 Kelvin. So really small, the Tc. And that is why research is going on how you can get a superconductor at room temperature, right? So if resistivity is zero, so resistance is zero, so that means you have, so while conducting electricity, there is no joule heating, so there is no loss of energy due to flow of current, which happens in all materials at room temperature. Or even if you have a little bit of resistance, so there will be always a heat loss when you flow a current through it. But if you have a superconductor, you don't have that, and that is why there is a quest. People are trying to find out or to synthesize a material or a superconducting material with Tc at room temperature. Okay, uh, so in case of metals, you can actually write down, so this typical behavior in case of metal. So let's look at this temperature dependence of metal a little bit closely. So what you have is, when you go to a higher temperature, so normally your rho would be proportional to T, directly proportional to temperature T. And but when you go to very low temperature, so it becomes a constant. So it doesn't go to zero, but it becomes a constant. So why it is that? So that is because the resistivity normally comes from, broadly one can say it comes from two effects. So one is a temperature dependent term, and another is a temperature independent term. And what contributes to the temperature dependent term? So temperature dependent term is due to, so this is called a temperature dependent term, and this is due to electron and ion interaction, or the atom interaction. So this and these interactions, or you can also have electron and electron interaction. So electron can get scattered. So resistance is due to scattering of the electrons, and electrons can get scattered due to this atoms or the ions that are present in the lattice sites. And why would it get scattered? Because of the, so these atoms, they are vibrating around their mean position, so they have a vibration, thermal vibration. So these electrons will get scattered due to those thermal vibrations. So you can also say this is a thermal vibration of the lattice, so to say. Yeah. So you can also have electron repulsion, but that is not the majority or the major reason for the resistivity of most of the material, but the major reason is the thermal vibration of the lattice or the motion of these uh, atoms. And then you have a temperature independent term, and this is normally due to you have impurities or defects in the crystal. If you have impurity or defects, so or like you can say these imperfections in the crystal, so they lead to a temperature independent resistivity. So that term doesn't depend on temperature at all, and therefore you see when you see these both contributions. So when you are at higher temperature, so at a higher temperature, you have, so this rho T term will dominate, okay, because the thermal vibration of the atoms will be much higher. So therefore these terms will dominate, and you see a clear temperature dependence of resistivity for metal. However, when you go to low temperature, so these thermal vibrations are not they reduce, and their contribution is less, and therefore you see the effect of this rho I when you are at low temperature. And therefore these resistivity becomes constant, which is a due to this you can say here this is like a rho I. This value would be rho I when you go to low temperature. So conductivity of an insulator should increase with increasing temperature. Yes. So when I say resistivity is decreasing, so resistivity, so conductivity is so okay. Anyway, so so conductivity is it's a reciprocal of resistivity. So that means when we say resistivity is decreasing as we increase the temperature, that is what happens in case of semiconductors and insulators. So in that case, conductivity will increase. Okay, so this rho, when we say this is like consists of two terms, rho T plus rho I. So this rule is known as a Mathiassen's rule. Okay, that is Mathiassen's rule of resistivity in metal. So when we say this, when we talk about conductivity in general, so in metal or even in semiconductor or any material, so we say it is due to the free electrons. So what do we mean by that? Uh, so we, so if you look at, for example, any metal, so you have, so let's say this is a solid. So this is a qualitative picture what we are showing here. So you have ionic cores. So this is what makes the lattice. Okay. And then you have the electron, which is basically probably the valence electron that comes from the atom. So which will be belong to the whole solid, and they are free to move anywhere in the solid. And these electrons, so these are the free electrons, so they are not bound anymore to the ionic core or any lattice, so they are free to move, and these loosely bound electrons basically contribute to the conductivity of the material. So they are the responsible uh, they are responsible for this conductivity of material. So if you have these free electrons, which in a metal, sometimes they are considered as a electron gas, because they behave almost like gas particles when we talk about kinetic theory of gases. So these are almost like free electrons or electron gas, which is responsible for the conductivity of the material, and they are also kind of responsible for the metallic bonding in this metallic systems. So these free electrons also are reason for the metallic bonding. So classically, we can actually quite well understood most of this electrical conductivity in metal. Yes, it is known as an electron gas. So why we call it a electron gas? Because similar to your gas particles, where you have where you can assign a velocity, a mean speed and mean velocity. So you can also assign a mean speed and velocity to these electrons, and therefore it is we call it a electron gas. Okay, so a free electron gas. Uh, so so this conductivity can be understood using a model known as Trude's theory. So if you are aware of it, I'm not sure if you know already about it, but I will briefly discuss about this Trude's model. So here again, I mean, Trude's model is based on basically the this kinetic theory of gases. So many concepts are borrowed from there. So that means, so one basic assumption is that these electrons, they do not interact. So there is no, so electrons do not interact with each other. So they are like this electron, this is a gas, which are not this gas particles, they are not interacting with each other. And the current density, so what basically when we talk about the flow of current, so we want to know what is the current density, and the current density can be written like J, so which is a vector quantity actually. So this is flow of charges through a cross-sectional area over time delta T. This is your, so delta Q is that net charge passing through a cross-sectional area A in time delta T. So this is the definition of current density. So if you, I think we have, I have a picture somewhere here. Let me see, yes. So this is what the picture would look like. So you have this according to the Drude's model. So you have electrons, free electrons, and now we have applied the electric field E, and due to this, so the electric field E is applied in this direction, and now due to the electric field E, so these electrons will accelerate in the opposite direction to the field direction. and due to this net motion of the electron, so you will have a current density. And now the cross-sectional area here, this is represented by A here. This is the cross-sectional area A. And due to that, so we have a current density J. Now, how do we, and this normally, this motion of electron due to this electric field is normally known as a drift of electron. Okay, so the name is drift of electron. So we say when you apply electric field E, the electrons will drift due to the applied electric field. So and this drift normally you can represent by a drift velocity. So we call this a drift velocity. This is an average velocity of electrons. So this is average velocity of over all the electrons due to the electric field E. So which we can write down as, so if we have n electrons, let's say, per unit volume, so we can say, so you sum over all the electron instantaneous velocities, and then you average over all the n electrons, and you get an average velocity. That is what we call as a drift velocity. So that means some electrons will move faster compared to this drift velocity. Some electrons will move slower than this drift velocity, but on average you have a drift velocity d. Okay, so now in order to calculate what is the relation between the J, our electron current density, and the drift velocity, so we'll do a little bit of mathematics. I think maybe you already know that. So what we need to calculate, what is delta Q. So this is the picture we have. Okay, so we want to calculate what is delta Q, delta T. So the cross-sectional area is A. So what is delta Q? Delta Q is nothing but, so how many charges are flowing, they are crossing this cross-sectional area A. So E is your electron charge, N is the number of electrons per unit volume, small n, and A into delta X. So what is A into delta X? That is basically your the volume of this cylindrical. So if I have, maybe I can plot it here again. So you have electrons which are crossing this cross-sectional area A, and in order to have a current density, so these electrons should pass through this area A. So this is A, and delta X is, this is your delta X. So to have a finite current density, so the electrons should pass from one end to the other end, and then only you will have a finite J, otherwise J will be 0. So how much charge is flowing across this within this volume, through this volume? So this is E into N A delta X. That is the total charge that is flowing through it. Okay, and what is delta X? Delta X will be the drift velocity into delta T. So the net displacement will be proportional to the velocity into time. So delta X will be the average drift velocity into delta T. And in that case, we can write down then J will be equal to, so if you substitute that, so J is delta Q by A delta T. So if you substitute this is A delta T, which is nothing but, so your A and A will cancel out, and delta X by delta T is V into B. So you have a direct relation between current density J and a drift velocity V. So they are, so the current density J is a macroscopic property, so that we can measure, the current we can measure. And Vd, that is the drift velocity, it is associated with the electron. Okay, so it is the, what we are saying is electron, it's a microscopic property. So it is directly related to the drift velocity of the electron. And that is what gives rise to a current density. Now, what is, so let's look a closer look at this drift velocity. So we defined Vd as, so we said Vd is 1 by n, and then we sum over all the electrons. So these are, what we are saying is all are free electrons. Okay, so all electron means this n are number of free electrons. Okay, so we are not considering other electrons which are bound to the atom or the core. So these are basically, you can say, these are the valence electrons in the from the atom. Okay, so this is the summation over this, and Vi is the instantaneous velocity of, let's say, ith electron. Now, what is this Vi? What is the ith electron velocity? So Vi, you can write it down. So this is all we are based on classical physics. So the this Vi, the instantaneous velocity of the electron. So what we are saying is what happens when just after a collision has happened, okay, or a scattering has happened. So the electron, when it travels through the metal or the material, so it will be scattered or will have a collision. So it can be collide with due to the thermal vibration or due to the impurity or defect. So it can be any reason this scattering can happen. However, this collision will lead to a instantaneous velocity, will give an instantaneous velocity v, which will be equal to ui plus, since we have an electric field E, this will be E by mE into T minus Ti. So let's look at these terms a little bit carefully. So what is Ui? Ui is, this is initial velocity just after collision or scattering. So electron will get scattered from maybe the atom or the defect, and just after it gets scattered or collides, so there it will have an initial velocity ui. However, this initial velocity, on top of that, electron will immediately experience the electric field as well. Okay, because there is, we have applied a voltage, so electron will experience this electric field, and that so here this is the force is basically the force on the electron will be E into E, that is the force. The force is E into E, and now the acceleration will be E by m. So that is the acceleration of the electron due to the electric field. And what is Ti? Ti is a time of last collision of ith electron. So what we want to measure or find out, what is the instantaneous velocity Vi after at a time t. So let's say we say at a time t, after it collides with, like it gets scattered. Okay, so this is what we want to calculate. So VIT will be UI, which is initial velocity just after collision, and that means UI is measured at time. So UI. So UI is at time Ti. So just when the collision happened. So this is at time Ti. And then what is the velocity after time T? So we say Ui plus the acceleration into T minus Ti. So the time elapsed between the time difference T minus Ti. So this is how you can understand, let's say, what is the instantaneous velocity just after collision. But when you look at closely, what is this? And now we have to calculate this Vi for all the electron and then sum it up, and then we can get the drift velocity. So, so let's say if you assume there is no electric field, let's say, so if E is equal to 0, so what will be the drift velocity in that case, or the instantaneous velocity? VIT will be nothing but Ui at Ti, let's say, because there is no any acceleration. However, if I take now, if I want to calculate what is the drift velocity, so now I sum it over VIT. Okay. Now, if I want to sum it over all these electrons, so Vd will be equal to 0 if E is equal to 0. Why? Because we know our J is proportional to the drift velocity, and if we don't apply any electric field, we know that there will be no current density. So without electric field, we will not have a current density. So that means J should be of, so when E is equal to 0, J should also equal to 0. That means there should not be any drift velocity of the electron. So Vd should be 0. And that is what we are writing here. So in absence of an electric field, this Vd will be equal to, the drift velocity will be 0. However, so this is the average velocity is 0, but the instantaneous velocities may not be 0. So this Ui may not be 0 because electron will have a initial velocity, and it is again getting scattered. It is not like electron is not getting scattered. It is getting scattered, and it has a certain velocity. There will be a velocity after it is getting scattered. However, there is no net drift velocity in a particular direction. Okay, so you don't have a particular motion of electron along certain direction. So this actually can be easy to understand when you look at this picture here. Okay, so the left one shows when E is equal to 0, and this is here we have electric field. We have applied electric field. So what happens if you look at this electron, for example? So after it is getting scattered, so it has certain velocity u, and then again now it moves, and then probably it will get scattered again and again and so on. So many things many scattering things are happening. But if I take the average of these velocities, and what I will see is that basically there is no net displacement of the charge from the initial point after in certain time delta t. Let's say when I'm observing the motion of electron in a certain time delta t, so there is no net displacement. So net displacement is always will be a zero, uh, uh, and therefore the drift velocity will be zero. However, on the right hand picture, if I say I am applying an electric field E now, so there will be this collision will be going on. So there you will have a instantaneous like velocities, and however over a time period delta t, so you will observe a net the electron has there is a net displacement, and it is not the vd is not equal to zero. So that is what you see. So when you apply electric field E, so you will have several collisions within this time delta t. However, there will be a net drift of electron from one point to another point, which is about delta x. And this is the difference when you have E equal to zero and or electric field, and you don't have an electric field. And in principle, this u, what we saw here, this u, initial instantaneous velocity just after scattering. So it can be positive, it can be negative, okay? And therefore, when you take the average, so you get a zero when there is no electric field. However, if you have an electric field, so this term will be non-zero, and therefore you will have a non-zero drift velocity. So we can write now this Vd, which is equal to 1 by n ui plus E by n t minus ti. So again, yeah, we have to sum over all. Equal to 1 to n. So if you do that, look at this, the first term will be always zero. This term will be zero because we are averaging over all the instantaneous velocities, which will always be zero. But we have only the contribution, non-zero contribution will come from this second expression, and which we can write down as so this is Vd. So we can write down this Vd will be equal to 1 by n, sum over I equal to 1 to n Te by n t minus ti, or sometimes it is written as E. So these are again constant terms. So one need to take the average over T minus Ti. And what is T minus Ti? So T minus Ti is the average time between two collisions. So this T minus Ti average, you can say, is the average time between two collisions or scattering.
Sir,
Yes.
sir, if you have taken the average of t minus ti, is there a need of 1 by n factor there?
No, I think we don't need to put it here. So this we can write that Te by n, so T minus Ti. Okay, so this is, we don't need to write n here. So this is the average time between two collisions or scattering, and this represented by a term tau. Okay, so tau is known as the average time between two collisions, or sometimes it is known as the mean scattering time, and also, so there are different names to it. So relaxation time. So what is this tau represents? It represents the average time an electron takes. Uh, yeah, so it takes between two, or the time it takes for the from one collision to the next collision. Uh, and that means within this time tau, this is the average time, within this time tau, so electron will not encounter any collision. So it will get accelerated due to this electric field without getting scattered. And this tau, uh, so in principle, this is an average time. Okay, so sometimes it can happen. Some electrons, for some electrons, this tau will be large. So that means the collision time will be large. For some electrons, this collision time will be less. But moreover, you will have an average time tau for all of the electrons when you consider all the electrons. And in that case, we can write down our equation, right? Et by Me into E, and which you can write something like this term E tau by Me is represented by mu D. So what is mu D? It is known as a drift mobility. So it is known as a drift mobility, and it depends on, of course, the electron charge or the charge carrier. What is the charge on the charge carrier? The mass of the charge carrier. In case here we have electron, and the relaxation time tau. And tau is related to the microscopic scattering processes. So tau is related to microscopic scattering. So we can write down now the J, which we said it is Ne into Vd. Okay, so and we have an expression for Vd, which is mu D into E. So we can write this as Ne mu D into E. So your J current density will be J is equal to Ne mu D, which is again a form of your Ohm's law. So if you rewrite in terms of V voltage and current, so you will get this Ohm's law, V is equal to IR, and this is a form of Ohm's law, where your sigma is your conductivity, which is given by Ne into mu D. Okay, so your conductivity of a material depends on what is N here. N is your number of electrons per unit volume. P is the charge, and mu D is the drift mobility. So this sigma, the conductivity that you normally measure in a lab, so you can measure the conductivity or the resistivity that you measure. So it is a macroscopic quantity. So it is a macroscopic quantity which is related to your mu D, the drift mobility, which is a microscopic quantity, because it is related to the drift of the electron. Okay, although we are talking about the average velocity and everything, but it is related to the microscopic picture. So so a macroscopic quantity that you can measure is related to this microscopic parameter, so to say, in a material. So why mu D is so important? So mu d is important because most of the electronic material, when we talk about electronic material and when we want to compare their properties, so normally we talk about their mobility. So what is the mobility of charge carrier in those materials? And particularly when we talk about this mobility in electronic devices or semiconductor devices. So when we discuss about electronic or semiconductor devices, so this mu d or the mobility is a very important parameter. And what it says, it says how fast the charge carrier, let's say the electron, will move in presence of an external electric field. How fast or how slow? So depends on if mu d is high. So if you look at the relation, yeah, so I mean, if you look at sigma, the expression for sigma, so sigma is your conductivity. So if mu d is high, mobility is high, so you'll have a higher conductivity. Or the probability that the charge carrier will move faster will be, so it will move faster if mu d is high. And therefore, when you make a device, you want to make sure that your mobility is high. However, mobility, and why do we want to make a higher mobility? So if mobility is high, so let's say if you look at the microscopic properties, so your mu d, it is proportional to tau. Okay, so mu d will be high if tau is large, right? Because mu d is directly proportional to t. So if mu d is large or high if t is large. So t is large means the collision, the time between collision is large, or the relaxation time is large. So you have a high relaxation time. So that means there are less number of collisions. Okay, so if you have less number of collisions, so the electron, when it goes from, so the time between two collisions will increase if the number of collisions are less. So that is what you want. So why you want a high mu d or high mobility? So if mobility is high, so your device will run faster because your communication happens due to this charge carrier movement, and since mu d is high, so device will run faster. Sorry. If mu d is high. And the typical, so this is mu d is the unit is centimeter square volt inverse second inverse, or millimeter square volt inverse second inverse. That is the unit. Yeah, so I will stop right now. If you have any question, since it is already time. So we will do one example in the next class about this device will run faster means the operation time of the device. So let's say if I have a transistor or a diode, now if the charge carrier moves faster, that means I can switch it on and off faster. Okay, because the information that I will send, or so the response to a change in voltage will be faster. Okay, and normally we control these devices by applying a voltage or maybe a current. Okay, so these are the external parameters which you use to control the device. Now, when you are applying this voltage, and if the electron responds really fast, so that means you can, so now you can vary or change the uh, flow of current. So we can make it so for example, for the diode, you can make it on or off faster. So that is the way of saying the devices will be faster. So in case of, let's say, if you take a MOSFET device or a field effect transistor, for example, so which normally you use as a on-off switch, because you want to switch between 1 and 0. Okay, so these are the things. So when you are making doing some calculation, or measuring or performing some logical, uh, like you are creating a OR gate or an AND gate or a NOR gate. Okay, so like logic circuits you are building. So what you want is like it should do this calculation as fast as possible, and it will be possible only when you have the electron movement is fast, or that means mobility is high. Okay, so that is why you want, or in that sense, we say that devices will be faster when the mobility is high. Okay, anything else? Okay, so if not, so thank you. Then we'll meet them tomorrow.